I want there's a math, of course, like everything else in this class, there's a way of mathematically representing something. You guys tend to get bogged down there, which is, I think, what's causing your problems. Maybe causing my problems. Maybe I focus too much on the math, or maybe I just assume that you have enough mathematical aptitude that the algebra isn't getting in the way. I'm afraid that it is getting in the way. I think you're looking at your notes and seeing just letters everywhere. And you're not, or maybe I'm not, but you're not writing enough information in between those to tell you why they're there and why we chose those specific ones. That was clear at the end of our sixth period yesterday, when we had a little extra time after the quiz, more than this class, and somebody asked very specifically, I asked very specifically, what's the problem? And the student said to me, clearly, I don't know when to use which equation. And if that's the case, then you haven't written down what I think you need to write down. Because you have an entire equation sheet, right? So obviously, it's not about the equations, and never has been. And let me just prove it quick. We're going to talk about center of mass first. And again, it's just a definition. But I'm telling you right now, it's where the average mass of the object is. It's a location. That's the first thing that people don't understand about center of mass, is that it's not the mass of the object. Center of mass is a location, it's a place. So in order to understand center of mass, you have to understand that it's going to be something in meters, right? It's going to be a coordinate. It's going to be an x direction and a y direction and a z direction. It's going to be something maybe within the object, maybe outside the object, I don't know. But it's where the average mass is. If I want to reduce the object to a point, that's where that point would be. So we sometimes think it's the middle of the object. But if I give you a paper clip, you realize that the center of mass is probably an empty space in the middle of that paper clip, right? Because it's kind of a donut, or even a donut would be a better example, perhaps, except it makes some people hungry, and then you start talking about food, and people get a little weird. But I think the center of mass of a donut would be an empty space. Wouldn't you kind of agree with that? Unless it's one of those cream-filled donuts, and then that would change it altogether. Or jelly-filled donuts. They'll have something there. So these are not good examples. I need better examples. So I'd say my cup because it's empty. I bet the center of mass of my cup is an empty space. But it's a location. Do you get what I'm saying? So for you guys, and for me, I want you to understand that it is a location. But there's still a way to find it. There's a mathematical way to find it. The problem is, what if I just told you that I want you to find the center of mass of this triangle? Right? Where the average. Let's say I cut a triangle out of a piece of wood, and I throw it on the desk. Where's the center of mass? One way of finding the center of mass is by finding its center of gravity. And these are two different things, but they're not really that different. Because the center of gravity is where we would say gravity acts on the object. It's the balance point. Now, gravity acts on the entire object. I want to be very clear. But if you can find a place to balance an object, you have found its center of gravity. If you throw something, the thing you throw will naturally rotate around its center of gravity. And it's a center of gravity that you can track as it moves. Because although, yes, if you have like this triangle that we have here and I ask you to find the center of mass, I bet you guys probably know that it's probably more this way and more this way, right? I'd probably argue that's probably somewhere in this area. That's probably reasonable. But it's a location. So in order to find the center of mass and do it mathematically, you have to establish a few things. Like, if I'm going to tell you where the center of mass is, I need to give you reference. Like, well, where's the starting point? If I say it's in its middle, well, I probably want to say that it is so many centimeters from this point, or so many centimeters from this point. And that would just be on the horizontal. There's also how many centimeters from this point, or how many centimeters from this point. So in finding center of mass, you start with providing reference. Where's 0? Where are you measuring the center of mass from? That's the first thing you have to do if you want to find the center of mass of an object, is pick a place on the object and make that 0. I would make one end of the object 0. That will help. Now, we're not going to probably do this one. We'll probably do simpler first. And the reason why we'll probably do simpler first is I'm going to show you how you calculate center of mass, and then you'll see why we're going to do it simpler. The way you calculate center of mass is, first, reminder, it's a location. So I'll use X, and we'll just do one-dimensional for right now. And you'll see why. Center of mass is an integral of x dot dm divided by the integral of dm. As the definition goes, throwing this in front of you isn't meant to scare you. This is what the definition looks like. And the moment I put the little curly Q S on there, that a bunch of you, your eyes just glaze right over. But remember, it's just a sum. And the top is a sum of a product, and the bottom is just a sum. In fact, the bottom should be easy. dm means a piece of the mass of the object. So if I add up all the pieces of the mass of the object, the bottom is just the mass of the object. The bottom's easy. The reason why it's written as an integral is a complicated thing about if you have an object whose mass isn't known, but you have an expression for its density. This is how you could find out what its total mass is. It's a holdover, and we will never use that. But the top we might. And the top is different. X is a location. X means where is that individual piece of the object. So if I wanted to describe what the top is telling me to do, and we want to maybe make the meter stick our reference for how this might look, we pick a place, call it 0, and then I would say, okay, right here, carve out 1 centimeter's worth of meter stick, and say right there, a distance x away from 0 is a little piece of the meter stick. So I take that 1 centimeter location and I find out how far away it is from 0. And I say, okay, multiply the mass of that piece by how far away it is from 0. And then pick another piece. Find its x away. And find out its amount of mass. And then take that piece and add it to the other one. And do that for every piece of the meter stick. Add them all up, and you'd get the center of the meter stick. This is the formula, if somebody might recognize this, but this is the formula for a weighted average. You've learned about weighted averages in Algebra 1, maybe even in middle school. But does that sound familiar, doing a weighted average, where some things contribute more to the average than other things? This is telling you that to find the center of mass, things that are further away from 0 contribute more to the location of the center of mass than things that are closer to 0. That's all that tells you. Now, we're not going to do this till you have a little bit more math behind you. And when we do it, we're going to do it for simple shapes. But this is on the exam. This is probably one of the harder topics for you guys who are not in calculus. It's been on the exam 3 times in the last 15 years. So it's not often, but when it is, usually they give you the answer so you can skip it. You'll lose the 2 or 3 points. Does that make sense? I want you to learn how to do it because it's not that hard. And everybody in the room will be in the same boat of not being able to do it because it's not about the calculus. It's about setting up what the DM is. That's actually the hardest part. How does this affect you guys if we're never going to do that calculation? Well, we're going to do a cheater way of doing that calculation. The way to do it with the math you do have. So that's what this semester is about. So let me start by saying that there's the calculus method and there's the point mass method. The point mass method is a simplification, but it's also the same thing just without calculus. Remember, this symbol tells you to sum, right? I've said that a couple times in here, so you guys do remember that, right? So add it all up. Calculus does it fancy, so if I don't want to do it fancy, the other way to sum is to use that symbol, right? You are aware of that symbol? And we've had a conversation about this symbol before, about how you're supposed to fill it in, all the parts. The bottom is the counter part, and the top is the ending point. So at the bottom, I could say I'm going to add something up. I'm going to add up the product of a location and a mass. It's a product. So I'm going to look for x1 and m1, and I'm going to add it to x2 and m2. I'm going to add that to x3 and m3. What I'm going to do is I'm going to take my object, I'm going to break it up into multiple pieces. M1, M2, M3. Now I'm going to break it up into multiple pieces, but I have to account for the entire object, so I have to have enough pieces so I take up every single piece. For example, I could break up the meter stick into 100 1-centimeter pieces. And then my summation would be the sum of all 100 pieces. You guys follow what I'm saying to do? Like, for example, the first piece would be located 1/2 centimeter from the start, right? Because the piece is 1 centimeter wide, the middle of that piece would be where I would measure it to. The second piece would be 1 centimeter away from that. And the next piece would be 1 centimeter away from that. You following along? I could break my object up into pieces. The summation then would look like this. I take every single piece, and I'm going to start with the first piece and end with the last piece. So for this, I'd start with centimeter pieces, so I'd start with piece number 1, and I'd end with piece number 100. Right? If I was breaking it up into lots of pieces. I think in your math class, you use the counter I, don't you? Have you guys done a summation recently?
Yeah.
Any of them? So your book, it changes the numbers all the time, but you could say it this way if you wanted to write a generic, meaning I'll use the counter as I, and N represents whatever number of pieces there are. But you have to start with the first piece and go to the last piece. Now, luckily for you, for most of the things we do in here, we only have maybe 2 or 3 pieces. We're not going to do summations like this often, and the summation version of this isn't usually on the exam. The only time they ever put on the exam is when they usually use the calculus version, the integral. But before I can teach you that, you guys have to know what we're actually doing. So we're going to do this real quick. We're going to practice one. We're not going to break this up into 100 pieces because I don't want to waste the time of you guys adding 100 things together. We're going to break the meter stick up into 10 pieces. Does that make sense? So 10 pieces means that you're going to add 10 numbers together. All right? I measured the meter stick's mass earlier, and it's 65 grams. So if it's 65 grams and we're going to break it up into 10 pieces, let's just assume that it's a uniform meter stick, so that each piece is going to be 6.5 grams. Does that make sense? You guys understand what I'm saying? If not, speak now. Okay, so each piece, 6.5 grams. There are 10 pieces. So I think we can all agree that each piece is going to be 10 centimeters wide. So where's the center of the first piece if I'm making this the starting point? 5 centimeters, that's right. The center of the first piece will be 5 centimeters away. Just to make sure we're all paying attention, where is the center of the second piece? 15, good. Now we see how we're going to increase our measurement each time. So take a minute. There are 10 pieces. I'd like you to calculate the center of mass of the meter stick. You're going to be multiplying and then adding 10 numbers together. But in the end, remember, you have to divide by the mass of the object. So the whole mass was 65 grams. Each piece is 6.5 grams. Now, so I'll ask politely, does anybody need help working this out? All right. Although bothered, I will do it because I am your teacher. And I try to answer questions. So, again, my top is a sum. And my first piece is 6.5 grams located at a distance 5 centimeters from 0. That's where this piece is. My second piece, also 6.5 grams, is located how far away from 0? 15. My third piece is 6.5 grams, located how far away from 0? I'm seeing a pattern develop. I think there will be some pieces in the middle, but my last piece will also be 6.5, and where will its center be? 95. That's right. There will be 10 pieces. Those are the 10 pieces. I left a few out because come on, I want to write it all down. Because I realized right away that I could factor out the 6.5 from all of them. I would encourage you to look for stuff like that, because then inside it's just a sum of 5, 10, 15, 20, right? No. 5, 15, 25, 35, 45, 55, 65, 75, 85, and 95. And that's what's inside. So if you add all those things up and then divide by 65, you'll get 50 centimeters. That's all this is. We did have to pick a place to take our measurement, and so picking the end made sense. We didn't have to, but we did anyways. Now, is that enough for you guys who are having trouble? Because you understand, I feel a little silly, but it's okay. Luckily, I didn't make you break it up into 100 pieces, because that would take longer. Now, we're already taking too long for this silly little exercise, so I'm going to move us along. But I do want to point out a few things. Center of mass is a location, which means it's a vector. By setting our starting point to be 0, we have made all of the mass of the object in one direction. If we had picked our measuring point somewhere in the middle, we would have had to have chosen one side to be positive and another side to be negative. So be aware that the real calculation is a vector calculation. And also, we don't have to do just one-dimensional objects. I can take my object and break it up into pieces in 2 dimensions. So when I'm finding, say, the x direction of the center of mass, I break it up this way. When I'm finding the y direction of the center of mass, I break it up this way. Right, I do it separately. Break it up once for the x direction and don't care about how tall each piece is. Then I break it up once in the y direction and do that again. Okay. Now, the reason that the actual center of mass function looks like this is because there are objects that don't have a uniform mass, that their mass changes depending on where you are in the object. Jupiter's cloud density gets thinner as you go further away from the center. So it doesn't have a uniform density. Because of that, you would have to integrate, knowing a formula for how the density changes. Most objects probably don't have uniform densities, and therefore this is the way you tend to calculate their center of mass. Also, not all objects are perfectly uniform in shape, and that's why we'd have to have the integration in case the shape influences the center of mass. So that's why that's there. Here, you're going to do one more for me because I want to know that you can practice. The Earth has a mass of 5.98 times 10 to the 24th kilograms. The Moon has a mass of 7.22, I don't know, 7 point, 7.37 times 10 to the 22nd kilograms. They are separated by 384 times 10 to the 6th meters. Where's their center of mass? I'd argue this is easier than what you just did because there's only two objects, so your summation is only two things. But I think a bunch of you are going to balk at this, like having no idea where to start. So I'll remind you, no matter how many things there are, you start by picking a place and calling it 0. That was the first thing I said to do, is pick your reference point. I think the best place to pick as your reference point would be the center of the Earth. We choose the reference point. Now my summation is going to have two things in it. I'm going to have the mass and the distance to the center of the Earth, and the mass and the distance to the center of the Moon. I have to divide by the total mass, which in this case will be the mass of the Earth plus the mass of the Moon. Giving you everything you need for this, and more now. This is how you calculate center of mass. So I've taught you how to do it for point masses, or how to break an object up into individual pieces. Take a minute though, because I want you to do this. At least have some practice, because you're going to see something real quick, I hope. So I did have a couple people say yes, they had trouble with that. So let's start by just moving this to the side. And if I chose this point as 0, what is the distance from the center of the Earth to the center of the Earth? 0. So my first location, my distance to the center of the Earth, is 0, because I chose 0 as my measuring point. I'm measuring this from the center of the Earth. And then I will multiply by the mass of the Earth, but I don't really need to write that number in, do I? So as a weighted average goes, the weighting on the Earth is 0 because I'm doing this relative to the Earth. Bless you. Now I need the distance from the center of the Earth to where my next mass is. Pretty sure that's going to be the 384 times 10 to the 6th. Then I need the mass of that other thing, 7.37 times 10 to the 22nd. All right, my top summation is done. Those are the things I have to sum together. Now I'm going to divide by. Well, I'm going to divide by the total mass. This is where I'll need the mass of the Earth. But that's basically it. Now, understanding where that is, let me help you out. This distance, the radius of the Earth, 6.37 times 10 to the 6th meters. Does that help you with some scale? Because that places the center of the mass of the Earth, or the center of mass of the Earth-Moon system right about here. About 2/3 of the way towards the surface of the Earth. The reason that's important is that's where the orbit of the Earth and Moon actually are. The Moon doesn't orbit the Earth. The Moon orbits that point. This is why the Earth wobbles in its orbit and predominantly helps with tides. So it produces a couple of other effects on the Earth, but the Earth actually orbits that point too, which means it's always getting a little closer to the sun, a little further away from the sun every month. It doesn't affect our temperatures, but it does affect other things on the Earth. Weather patterns, stuff like that are all affected by this wobble. We're one of the only planets that does it, by the way. The only other one that does it would be Pluto and Charon. Every other planet that has a moon, the moon is significantly smaller than the planet. But the Earth-Moon system is unique, it's weird. And this is part of the weirdness. Having a moon so big, it causes your host planet to wobble. Point, maybe to myself, if not to you. Each one of these things should have meaning to you. Right? They all have meaning to you. They're used in specific circumstance. What's important, what I want you to recognize is that they didn't come out of nowhere. In this class, in our lecture, each one of those was clearly derived from another first principle. I didn't pull them out of thin air. We derived this by doing work on lifting an object. We specifically defined potential energy as work done by a conservative force. The difference between what's on the left side and what's on the right side is the left side is either a definition that we as physicists have established as part of what physics is about, and the right side is an implication of that definition or law. I mean, another one is right. This is a law. We showed where this law comes from, directly from the idea that if you have an unbalanced force, it causes an object to accelerate. That acceleration is a change in the speed of the object, resulting in a change in the kinetic energy. We derived it in class from first principles, right from Newton's second law. Again, this is a principle, a definition that we could derive. That's the left side. The right side is an implication. Right? The idea that, okay, how do we measure that change? We can measure it by looking at the velocity. And all of that came from the idea that forces are ways in which an object's energy is changed. We defined it by work. We gave a name to it. But the left side proved the things on the right side, derived them from a first principle. And then often, because force was involved, we were never very far away from Newton's first or second law. Now you're saying, I don't know when to use which equation. I believe you. I believe you completely. Because you don't know where they come from. And you don't know the difference between what a first principle is and something that's been derived from a first principle. That's why that's where your disconnect is. You believe that if I can find the magical formula, it'll just do the problem. Have you noticed that never works out in here? This is not your math class. It feels like your math class because we're always doing math. But the difference here is that you're not going to just be able to plug and chug your way through it. It's just never going to happen. So how do I know when to use this? Well, did the object's height change? Right? Isn't that all about height? I mean, when do I use this? Is there a spring involved? If there isn't, you're not using that. Is it moving? I mean, it seems like there's some obvious times. That's not really what you mean. I don't know when to use which equation. You don't know how to bring them together. I think that's more what our problem is. And like I said, I agree. I believe you.